Quiz 1, Tuesday of week coming. You get the entire duration of the discussion class. So don't be late, because if you're late, you lose time. And I imagine by now, you've all recognized that on the Sakai website, where we keep grades and stuff like that, there's a large collection of past quizzes and exams from previous 46 courses which I have taught. And all this stuff is available for your use as reference and study, as you see fit. Students on occasion come about and say, can I get some extra questions to work on? Some extra problems. Oh, there's enough there to keep you busy for a long time. And profitably so. But keep in mind, the way to benefit from that information is to examine any quiz or exam as if you don't know the answers and work them out. Then check the answers. It's all provided. And if you want answers for which explanations are provided, you'll see that the second half of each quiz will contain such questions and answers. Part of a quiz is multiple choice because our exams, unfortunately, in spring and fall, are limited to multiple choice option. A terrible method of examination. We don't have the time available to do what I consider to be real exams, the likes of which I give in the summertime. But if you look at some of the summer exams, you'll see questions and problems, the likes of which you'll be faced with. But for those questions and problems on the summer exams, the explanations are provided because the answers are written out. Now then, today we start to get into the real nitty-gritty of acid-base chemistry. But just before we tackle that, let's complete this consideration which we talked about last time. The leveling effect means that if you do Bronsted-Lowry acid-base chemistry in any particular solvent, our main concern is such chemistry studied in water, the strongest acid present, the strongest acid that can exist at high concentration, the strongest acid that can exist at high concentration in any solution will always be the conjugate acid of the solvent. For water, that's hydronium ion. Because any acid which is stronger than hydronium ion will react with water to an extent which is practically 100%, like HCl. So the dissolved acid, which is stronger than hydronium ion, in the specific example HCl, all goes away and converts to hydronium ion. So the leveling effect means that any acid stronger than hydronium ion is leveled to hydronium ion, which is really a way of saying it's converted to hydronium ion. Same applies to strongest base, which can be found in high concentration in a solution. It'll be the conjugate base of the solvent. So for water solution cases, that's hydroxide ion. So to get a little bit further with this, I ask you to recognize that some novel acid-base reaction studies have been done in solvents other than water. I've picked a couple cases just to see if you understand this leveling effect and understand the fundamental aspects of conjugate theory. If you want to write the formula for a conjugate acid of a molecule, you add H plus to the formula for the acid, but in a systematic, chemically sound fashion. What's that mean? We'll take a look in a moment. And if you want to write the formula for the strongest base, which can be found in high concentration in a solvent, you write the formula for the conjugate base of the solvent. So that means in a systematic fashion, you have to examine the structure for the solvent molecule and subtract from it H+. The examples will tell you what this means. That's why I wanted you to tackle the examples. Indeed, it's true that although just about all acid-base chemistry studies are done in water, some have been done in liquid ammonia. This has to be done at low temperature, because this stuff has a boiling point of minus 33 centigrade. Now that doesn't mean you have to freeze the entire laboratory, but it does mean you have to keep the system which contains this as your solvent at low temperature. Okay? Well, we started you off with this last time. Ammonium ion is the conjugate acid of this, and H2N minus is the conjugate base of this. Clearly, if you write the Lewis structure for the solvent molecule ammonia, because it's the solvent if I'm doing acid-base chemistry studies in ammonia, the only place H plus can add is to this non-bonding electron pair on the nitrogen atom. Now likely in 2045, because the textbook does this, you used a pair of dots for non-bonding pairs. I don't do that. Nothing wrong with it, but I can write this quicker than I can write the two dots, and I'm up here writing passionately and furiously with chalk, and half the time I wouldn't know the difference between a dot that's chalk and a dot that's an electron. So I don't use dots unless I'm dealing with a Lewis picture for a radical. Remember what a radical is? What's a radical? A radical is a paramagnetic species. What's that mean? That means it's a species which has got one or more half-filled orbitals in its valence structure. Half-filled orbitals means one or more unpaired electrons. In that case, I'll have to use dots. Pardon me. But if I have a species which has no unpaired electrons, I'm just going to use these electron pair representations, this stick. You're familiar with that. All right? And if I look at this, to generate the formula for the conjugate base, I've got to liberate H+, and all the NH bonds are equivalent, so it doesn't make any difference which one I break. And I break it heterolytically. That means as H+ leaves, the previously bonding electron pair now becomes part of the valence environment of nitrogen, which generates a minus charge on nitrogen. Okay? And when I put the H+ on the nitrogen, this generates a positive charge on nitrogen, which is one more reason why the ammonium ion should be written like this, not NH4+. That's just chemically unsound. And, as you know, when I break this bond, it is entirely likely that if I break the bond heterolytically, the electron bonding electron pair, which now becomes a non-bonding electron pair, is far more likely to wind up in the valence environment of nitrogen rather than the valence environment of hydrogen, which would create H- the hydride ion, because nitrogen is much more electronegative than hydrogen. Electronegativity, a very important concept. Now I know you all heard about electronegativity in 2045, but I'm curious how many of you know what it really means. A working definition for electronegativity is that it is a measure of the ability. You don't have to hurry up to write this down. We'll say it many times. It's a measure of the ability of a bound atom, not a free atom. When I measure the ability of a free atom to attract electrons, I'm talking about electron affinity. We're not concerned with that. We're talking about bound atoms. and how effectively they attract valence electron density to themselves. What measures that is electronegativity. How effectively does a bound atom attract electron density to itself? The greater the electronegativity, the greater the electron density attraction effect. Upshot, when molecules develop negative charge, you expect the negative charge, if at all possible, to be a resident of the valence environment of the atom in the molecule, which is of highest electronegativity. So with that, I left you with these two. The methanol molecule. And these are structure considerations. So I wrote, to answer this, to get at the correct formulas for the strongest acid, strongest base, which means write the formula for the conjugate acid of this, write the formula for the conjugate base of this. Same applies to this. You got to pay attention to Lewis structures. You already responded correctly when I asked the question, what is by far the most important property of any species? You said structure. You're right. We pay attention to structure more than any other property of a molecule. Because with structure, we can answer more questions about how this molecule will behave chemically. And that's what we want to do. If you need help in writing Lewis structures, because you need to be pros at writing Lewis structures throughout this term. If you need help in this endeavor, it's all in the Chem Notes, chapter 23. Everything I need and want you to know about writing Lewis structures is in chapter 23 of your Chem Notes. If you take a look in chapter 23, you'll find it. All right? Here comes H+. Where's the H+ going to land on this? Well, I only see non-bonding electron density on oxygen. So the only valence electrons of this molecule which are ready to make a bond with H+ are either of these non-bonding pairs. So I shouldn't be surprised to realize that the strongest acid which can be found at high concentration, if I choose to do Bronsted-Lowry acid-base chemistry studies in this stuff as solvent, this is methanol. I don't care about its name, that's why I didn't write it down. H3COH. This tells us a whole lot more than its name, and this tells us a whole lot more than this, because this gives us its structure. Okay? And this puts a positive charge on oxygen. All right? That's conjugate acid. Now let's go back to the parent molecule and write the formula for the strongest base which could be found at high concentration. Strongest Bronsted base which could be found at high concentration in this liquid uses solvent. Well, now I've got to make a decision. Because I can lose H as H+ by removing the hydrogen atom that's covalently connected to oxygen, or I can lose H as H+ by removing one of these hydrogens which are covalently connected to carbon. So now we've got to make a decision. Which hydrogen atom is far more likely to be lost as H+? A carbon-bound H or this oxygen-bound H? The oxygen-bound H. Why is that true? Well, let's take a look at the results. If I were to lose H as H+ from a carbon, from the carbon atom, okay, I would generate a minus charge on carbon in so doing, as H+ floats off into the system. On the other hand, if this H is lost as H+, just like for water, this generates a minus charge on oxygen. So now you have to make a decision. Which minus charge will be stabilized to the greater extent? The minus charge on carbon or the minus charge on oxygen? On oxygen, because oxygen is more electronegative than carbon. Done! See, already we're seeing how powerful this electronegativity tool is, or consideration is. We're seeing its utility as a tool in making this decision. All right? This is called a methoxide ion. Again, I don't care about its name. That's not important. The formula is far more important. All right, let's look at this molecule. Now, as H plus approaches, I see two possible points of attachment. Well, actually three. Here, here, and here. Well, these electron pairs are equivalent. So regarding attachment to atoms, the H plus could make a bond to oxygen or it could make a bond to nitrogen. So now we got to decide which bond will be made. Get out your acid-base table. Because to this, we're going to make an analogy based on information which is contained in your acid-base table. You see this nitrogen atom? What's the hybridization of this nitrogen atom? I'm listening. What is the hybridization of this nitrogen atom? Nope. What is it? sp3. What is the hybridization of the oxygen atom? What is it? sp3. How about that? Statement. If you don't remember, when you're looking at a Lewis structure and you wish to identify hybridization schemes for the central atoms of the molecule in the Lewis structure you've written. Okay? You count the number of sigma electron pairs in the valence environment of that atom. That's what you do. Remembering that at each and every covalent bond site, how many sigma electron pairs are present? At each and every covalent bond site, how many sigma electron pairs are present? One. If you look, for example, at the nitrogen molecule, there's a triple bond, but only one of those bonds is sigma. You learned about this in 2045, so let's put it to use. At each and every covalent bond site, there's one and only one sigma bond. So that'll give us a sigma electron pair for each bond site for which the atom in question is involved. N non-bonding electron pairs are strictly and exclusively part of the sigma system, so they also count as sigma electron pairs. That's it. One sigma pair at each bond site, and each non-bonding pair is sigma. So, 1, 2, 3, 4. 1, 2, 3, 4. So the atoms in question each have 4 sigma valence electron pairs. How does that result in sp3 hybridization? An sp3 hybrid is a blend of a homogenization, a mix of how many atomic orbitals? What does the sp3 symbology mean? Did you talk about making hybrid orbitals in 2045? Well, let me give you a brief story about how I talk about making hybrid orbitals. First, I put myself in the butcher shop. I'm going to make sausage, because I make hybrid orbitals just like I make sausage. I'm going to take a pound of beef, which by itself is pure beef, and a pound of pork, which by itself is pure pork. I'm going to take my meat grinder, okay? And I'm going to jam the pound of beef and the pound of pork into the meat grinder at the same time. And I'm turning the crank. I'm mixing up the beef and the pork. I collect all that I mixed. How much sausage do I get? 2 pounds. 2 pounds, right? Because I ground up a pound of beef with a pound of pork. And now I have a mix. a sausage that's 50% character beef, 50% character pork, right? So I make hybrid orbitals the same way. Except that I make hybrid orbitals in accord with how many sigma electron pairs I have to provide parking place for. A home in space, if you want, for an atomic electron. 4 sigma electron pairs each, right? So I'm going to grind up how many orbitals? 4. And when I grind up orbitals, number 1, in an energy level, I will always start with the atomic orbital that's of lowest energy. What is that orbital? S. But I got to grind up 4 orbitals. And in any energy level, there's only one S orbital. It's a single orbital sublevel. So after S, I have to pick the next orbitals with regard to relative energy. After S, what are the next collection of orbitals? P. And if I needed more, I go to D. Okay? We'll leave out F because they're really rarely part of the bonding or valence environment of an atom. Okay? How many p orbitals in the p sublevel? 3. And 5 d orbitals in the d sublevel. Okay? But in this case, I need 4. I need to grind up 4 orbitals because I got 4 sigma electron pairs to accommodate. So I take my s orbital. Specifically for nitrogen and oxygen, it's a 2s orbital, isn't it? Because these atoms live in period number 2, which means their valence environment is defined by energy level number 2, right? 2s and 2p. So I take my 2s orbital, now I got an orbital grinder, not a meat grinder. Now I'm not in the butcher shop, now I'm in the chemistry shop, the hybrid orbital shop. I take my 2s orbital, and I need 3 of the p orbitals, so I take all the 3 from the 2p sublevel. That's 2px, 2py, 2pz. Shove them in, and I grind and grind and grind and grind. How many orbitals do I get? The number of orbitals I get is equal to the number of orbitals I ground up. 4. What? None of these orbitals anymore is pure s or pure p. I mixed up an s orbital with 3 p orbitals. And I symbolize that by writing sp3. And I now have a hybrid orbital, which is how much percent s character? 25%. And how much percent p character? 75%. Bingo. That's how I play this game. That's all there is to it. I've seen textbooks that want to talk to you about wave functions and all that stuff. Nuts to that. We don't need that. You're making a problem which can be quite simple and should be simplified to the extent that it can be in first-year chemistry. The hell with the wave functions. Leave that for the people who want to do chemistry with computers. Now then, what I've done this for is to get you to realize. Here comes the analogy part. Here's the ammonia molecule. Has a nitrogen atom with a non-bonding pair, just like this N atom. How's this N atom hybridized? sp3, like this one, isn't it? Here's a water molecule. Contains an oxygen atom with 2 non-bonding pairs. Isn't that like this one? How's this oxygen atom in the water molecule hybridized? Is this sp3 also? So guess what? If we can use the acid-base table to answer the question, which of these is the better H plus grabber? Then we can answer the question for this molecule. Which atom with its non-bonding electron density will preferentially bond with H plus? Will it be the N atom or the oxygen atom? Are you looking at the acid-base table? Which is the better H plus grabber? Is it ammonia or water? Look at the table carefully. Which is the better H plus grabber? Which is the stronger Bronsted base, ammonia or water? Which is it? Ammonia, you betcha. So now I know the correct formula for the conjugate acid of this thing, the acid which can live at high concentration The strongest acid, which can live at high concentration in this liquid if I use it as a solvent, is this, which has a plus charge on nitrogen. Put another way, I ate the eraser. Oh, there it is. Which atom, N or O, has the lower electronegativity? N. So which atom is more willing, so to speak, to share its valence electron density with another atom? N. Because this thing stabilizes its non-bonding electron density to a greater extent than this, because this has a higher electronegativity. This is a greater electron density hog than this. So this is less willing to share its non-bonding electron density, which accounts for why ammonia is a stronger base than water. That's it. All right? Now let's talk about the correct formula for the conjugate base of this, because that is the base which can exist at high concentration. The strongest base which can exist at high concentration if I do acid-base study in pure this as solvent. Now, I can lose H as H plus from a carbon-bound H. I can lose H as H plus from this nitrogen-bound H. Or I can lose H as H plus from the oxygen-bound H. Now, as we recognize with this molecule, if I lose H as H plus from one of these carbon-bound H's, I make a minus charge on carbon. If I lose H as H plus from the nitrogen-bound H, I put a minus charge on nitrogen. And finally, I will put a minus charge on oxygen. Where is the minus charge stabilized to the greater extent? On oxygen, because oxygen is? How about that? And its electronegativity is a marvelous tool. Now I'm going to ask a dirty question. Did you do anything like this in 2045? I've told them time and again, when you do electronegativity, this is the stuff you have to do because it makes electronegativity real. It makes it understood. It conceptualizes electronegativity. It gives it real meaning. I can't get them to cooperate. You think I do this in my 2045 class? I wouldn't be without. You can leave the damn wave functions out by the trash barrel. I don't need them. But this I need. And so, we now proceed to the first general meat and potatoes aspect of Chapter 18 Chemistry. How to write equations for Bronsted-Lowry acid-base reactions. And to assist you in this matter, beside the acid-base table, which you already have, I've given you this handout. The acid-base table, in short order fashion, allows you to examine all the acids whose chemistry we will consider, and all the bases whose chemistry we will consider, and compare the acids from a relative strength standpoint, and compare the bases from a relative strength standpoint. We already did that, what we just looked at. Now we're going to do it some more. And use this information in conjunction with principal system inventories to be able to express in the simplest possible direct fashion the chemistry that takes place when a reaction occurs. What's the simplest, best way to express the chemistry that takes place when a reaction occurs? What's the simplest, best way?
Equation.
Write the equation for the reaction. Ha ha! So we need to know how to write these equations for reactions. And here, I'm sorry to say, is where the textbooks just fall flat on their face. They don't do this correctly at all. Which is why I don't use those damn things in here. They stand in the way of learning, and I'm not having that. Here we go. Rules. When section 18.6, specifically on page 18.5, with reference to the notes. Write PSIs. How do we write PSIs? Bingo! And after we've written the PSIs, for each substance or system we are considering, and the systems which we will consider will be solutions. You look at the PSIs after you've written them, and you do a real tough thing. You pick out the formula for the strongest acid in this from the PSIs. How do I recognize what's the strongest acid in the PSI? Well, I haven't memorized this yet, but I do have my acid-base table, don't I? And so I use the acid-base table like a crutch. You get this on every quiz, every exam. Because my interest is not having you memorize that stuff. It's having you use it correctly. If you do this stuff for as many years as I've done this stuff, you'll see that acid-base table in your noggin. Sometimes I dream about it at night. Helps me sleep. Because I like it. It's very wonderful information. Okay? Maybe that will happen to you sometime. But for now, we're just going to use that acid-base table information like a crutch. Use it as we need. And from this PSI, we pick out the strongest base. Because our horse sense tell us. The PSI tells us the principal components of the system. Clearly, if any acid-base reaction is to occur, if any H+ exchange is going to occur in the system, it's got to involve the strongest acid in our list and the strongest base in our list. What could be more obvious? And so, with that, we write the equation for the reaction. Then we do one last thing. We comment on reaction extent. And to simplify extent analysis, we'll list the reaction extent as large or small, no more, no less. Large, if the product acid is weaker than the reacting acid. We expect the reaction extent to be large. Because you've gone from more reactive to less reactive. And that's the way matter behaves. In any environment in which you place matter, the matter will always behave so as to achieve the greatest degree of stability which it can achieve from a thermodynamic standpoint. That's the way matter behaves. On the other hand, if the product acid is a stronger acid than the reacting acid, then we shall expect the reaction extent to be small. Now notice what I've just said accounts for the resulting PSIs for water solutions of strong acids versus weak acids, as well as water solutions for strong bases versus weak bases, all of which you see on this sheet. Right? Okay. Okay? Here are the examples brought to our attention by question 1810. Let us begin to wrestle with these examples. A says, consider mixing the pure stuff, HCl gas. It's not a solution, not a mixture, with nitric acid solution. So before we go further with this, what do we have to do? We need to write the PSI for nitric acid solution. Write it. PSI, nitric acid solution. When you use the acid-base table, because remember you got to use that in conjunction with this, until you memorize it like me. You see that nitric acid is found to be a stronger acid than hydronium ion? See that on the acid-base table? That means when I make a water solution of nitric acid, the nitric acid will react with water to an extent which is practically speaking how much? 100%. So how does the nitric acid solution inventory? Hydronium ion, because that's what you get when any acid protonates water. The conjugate base of the nitric acid molecule, which is nitrate ion, and of course the solvent itself. So we've done the inventory. We got the PSIs. Now we can write the equation. So we're mixing up this system with this stuff. Now what's the rule of the road? Here's my PSIs. What's the strongest acid in this PSI collection of formulas? HCl. What's the strongest base in this PSI collection of formulas? Look at the acid-base table. Water. Interesting, isn't it? Because nitrate ion, like chloride ion, are each species that have formal negative charges, yet they are not as effective H plus grabbers as the water molecule, which is neutral. So, H plus exchange occurs. At this stage of the game, you may find it beneficial to label the reacting acid A, the reacting base B, and the product acid A and the product base B. Because each and every Bronsted-Lowry acid-base reaction involves formation of a Bronsted acid and Bronsted base, which are different from the reacting acid and base. And then the last part of the puzzle is extent. So once again, we use the acid-base table. And we compare the strength of HCl, the reacting acid, to hydronium ion, the product acid. You can do the same thing with bases. Reacting base water to product base chloride ion. Which one is stronger? HCl is stronger. That tells us the extent is large, done. And practically speaking, it's 100%. But again, to simplify this, because we'll worry about these percentages when we get into the arithmetic part of this game. We're not doing the arithmetic part now. We're just doing the qual part. Because you got to do the qual part, the conceptual part, before you do the arithmetic part. Oh, we go to B. This is A. All right? 1 molar HCl. Now, this reaction has already created for us the PSI for 1 molar HCl, which is a PSI we're already familiar with because we've talked about this before. It's hydronium ion, chloride ion, and of course water. There's our HCl solution. Notice the difference. In A, we're using pure HCl. In B, we're using a solution of HCl. PSIs are big different. Mighty big difference in this PSI. And ammonia solution. Tell me right now, the PSI for ammonia solution. You tell me and I'll write it down. We'll start with this because that's always part of the PSI for any solution. What is it? Nope. There's our PSI. Categorically, is ammonia a weak Bronsted base or a strong Bronsted base? It is weak or strong. Look at the acid-base table. Ammonia is a weak Bronsted base. It's weaker than hydroxide ion, which guarantees it's a weak base, but stronger than water, which guarantees its ability to function as a base can be measured in water solution. That means when ammonia reacts with water to make ammonium ion and hydroxide ion, which accounts for ammonia being a base, because on dissolving ammonia in water you make hydroxide ion, you make the pH go up. The extent of that reaction is small. So the main ingredient of ammonia solution, beside water, is the ammonia molecule itself. Okay, we got the PSIs. Pick out the best acid, strongest acid. What is it? For B. Here's our PSIs. hydronium ion. Strongest base? Ammonia. All right, reaction occurs. We make ammonium ion and water. So, in this case, hydronium ion is the reacting acid. Ammonia is the reacting base. Ammonium ion is the product acid, and the water molecule is the product base. Last part of the puzzle is extent. What's the extent? Large or small? This is a good deal stronger acid than this. Enough said. Large. All right? Now let's finish with C. And we'll pick it up from this point on Monday. Because everything we get through on Monday, that's fair game for Tuesday. Now, when we look at C, you must recognize there are two parts to a system inventory. So far, we've only looked at the qualitative part. The qualitative part is what you got. But on occasion, and often times, we have to pay attention to the second part of the inventory. What's the second part? How much? And in chemistry, we express how much by writing what? Moles, not molarity. Molarity tells us nothing about how much. That's a ratio. Amount, moles, that tells us how much. Okay? C. Sodium hydroxide solution. Quickly. Sodium hydroxide is an ionic compound. It's a salt. And like all ionic compounds, when they're dissolved in water, what do? They associate. So here are the component ions put in the solution by dissolving sodium hydroxide in water. And the other stuff is sulfuric acid molecule. 1 molar. Is sulfuric acid molecule a stronger acid than hydronium ion? It's even a stronger acid than HCl. So, here's our PSI for the sulfuric acid solution. Remember, nitrate reacted with water, practically 100%. The sulfuric acid molecule reacts with water 100%. Makes us hydronium ion, and this, the conjugate base of the sulfuric acid molecule. So here's our inventory. Pick out the strongest acid. That's easy. That's hydronium ion. Pick out the strongest base. That's easy. It's hydroxide ion. So one of the reactions with which we are concerned for system C is this reaction which we've already seen before. Extent is large. In fact, right now you can quantify this extent. What's the numerical value which corresponds to the extent of this reaction? The numerical value which corresponds to the extent of this reaction. 1 times 10 to the 14th. Because in the other direction this is kW, isn't it? And that's 1 times 10 to the minus 14. So I got it in this direction, the opposite direction. So 1 times 10 to the 14th. Do you think that's pretty large? My golly, it's only 100 trillion. You're damn right. Now then, remember, 2 equations. So let's finish this one because this is important. Notice, in the system we prepared, these are each 1 molar. But this is 2 milliliters. This is only 1 milliliter. So after I have run this reaction, which system component has been killed completely from a practical standpoint? Is it hydronium ion or hydroxide ion? Hydronium ion. So now, from my PSI, I line this out. And I go back to the PSI. And I re-examine. Because I've been directed to recognize there are 2 equations here. So I look at my list and I say, now what's the strongest acid? What is it? See this? It's right underneath hydronium ion in the acid column. And my strongest base is It's still hydroxide ion, because I only killed half of it in the first reaction. So now I'm looking at a reaction which makes water and sulfate ion. Here's my reacting acid, here's my reacting base. Here's my product acid, here's my product base. What's the extent? Large. You got it. We'll pick it up from this point next time.